So, thank you for joining us on this webinar. And on this webinar, we will talk about the use of the ACD iLab interface. As I say, it's an introduction for chemists that will want to use it as part of their work. So, to begin with, how do you access the iLab? You go to cds.rsc.org and you see a screen like this. You need to click the iLab button, and this will bring you into the iLab server. Now, if you are logging in from an academic institution in the UK, you will be directed straight to iLab. If not, then you will be directed to a login screen. And if you have been given details, username and password, you may enter them here, or you can authenticate. This is something that we need to discuss with your IT people or with RSC. Now, ACD iLab can do quite a few functions. So it offers an NMR database and prediction. It offers physicochemical predictions. It offers predictions for ADME and toxicity, and also naming of compounds according to UPAC. On this webinar today, we are going to talk about NMR database and prediction. iLab works on, is a web-based program, and it works on Windows, it works on Mac, it works on Linux. It's compatible with Internet Explorer, Safari, Firefox, and Chrome. Now, I have a little asterisk here in Chrome because there is there are some functionalities that do not work correctly in Chrome due to the security restrictions of Chrome. For what I will show you today, I will be using Firefox. Okay, and I think that's what was my presentation. And here we are now on Firefox, and we have the cdsrsc.org, and I'm going to click the iLab. And since I am not inside the UK academic institution right now, I have to log in. And after a bit, we see the main screen of iLab. So you can see here an area which is very animated, and this is where the structure goes. On the left, you can see the options for the predictions that you can have with iLab. Okay, so the first and most important thing is to enter the structure. So we'll spend the next few minutes showing to you how to enter the structure. In principle, there are 5 ways you can enter a structure. You can enter it as it shows on the top. You can enter it by drawing the structure manually, or you can enter it by uploading a file with structure information. You can paste a molecule from the clipboard, and this is now where the Chrome functionality doesn't work. So if you are using Chrome as your explorer, you will not be able to paste a molecule from the clipboard. Or you can submit the structures as a smile string in Smiles notation. And in any case, the first time you run the software, the first time you access iLab, you will see a lot of warnings for Java and security and whatever. You should accept all of them, and then it should work fine. So let's see how we can draw a structure from scratch. So we click this pencil icon here, and we are presented with a structure editor. And here we see some tools, some atoms on the left, and some ready-made templates, and some other tools up here. So let's start by taking an aromatic ring, and we put it here. And let's say that now I want to add a few more carbon atoms here. I click the carbon, and I just click on the ring and move my mouse a little bit, and leave the mouse, and it's there. And I click again and move it like that. So this is the way to enter one atom at a time. If I want to enter another atom, if I want to make, for example, a carbonyl there, and I select the oxygen, I go to the carbon, click and drag and leave the mouse, and I have an OH group. If I go on the bond and click on the bond is converted to a double bond. Okay, in the same sense, if I had a carbon, I could convert it to a triple bond. So let's make a few more things here. And now, so you see I did a mistake here. I didn't click on the atom. If you do a mistake, you select the eraser tool from here, and you select it, you see a square appears, and you click again, and it's erased. You click again there, and it's erased. So let's try again with a carbon. So click and drag, and click and drag. And let's put another oxygen here so as to make a nice aspirin molecule. Now, if you want, if somehow this structure doesn't look nice and clean, and the bond angles are not nice and whatever, you can click this green double arrow button to clean the structure, and you see the moment I click it, the structure looks a little bit more normal with all the bond angles set correctly as one would have drawn them. If for some reasons you don't like the way it appears like that, you can click the clean again, and it will go to another option for a clean structure. Okay. Now there are a few things that you can do here. Of course, yeah, you can add other elements. A very important function is the undo function. So if you undo, you go back to where you were, or you can redo. Okay, as with most software. We saw the eraser. There is the select tool. There is the clear all tool. So if you click this, everything will be erased. Yeah, another tool that may be of benefit is the chain tool. So if I select the carbon atom and I select the chain tool, if I click here and drag, it automatically draws a chain. Okay, so you don't need to go explicitly and put each single atom on the chain. And now there is also this tool here. So if you wanted to have, let's say, in between here another atom, you select here to add the node, you select the bond, click on the bond, and click on the bond, and you get it. It is already here. Okay, if I go to clean the structure, you will see that there has been one more bond added. Maybe we'll see it better in another example. In the same sense, you can remove a node. So if I go here, it chops it off. Okay, so let's undo all these and go back to the simple molecule. So once you are done designing the molecule, like of course you can make it bigger or smaller if you want, or view it from here, bigger or smaller, depending on how big is the molecule you are drawing. You click submit, and the molecule now appears in the structure area here. Okay. If you want to start predicting NMR properties, the simplest thing to do is just expand the NMR panel, and here you are presented with the options. So you can predict the carbon NMR spectrum, the proton NMR spectrum, the fluorine, the nitrogen, or the phosphorus NMR spectrum, or you can look into the various databases which we will see later. Okay, so let's predict the proton NMR spectrum of this molecule. So I click on it, the screen goes gray, and you see the loading button turning around, and after a little bit you see the proton NMR spectrum appearing. Okay, if you want to zoom on it, you can click and drag with the mouse, and it expands. Okay, if you go on one peak, you see automatically on the left-hand side of the screen the atom corresponding to the peak being highlighted as red, and also on the table showing the shifts and the coupling constants, the relevant lines are highlighted green. Okay, if you want a tricky thing to keep in mind is that if you want the peaks to go further, to be taller, you cannot do anything on this window. You have to go on top here on the preview window and lower the zoom box down, and this makes them bigger. Okay, now some options that appear here that are worth discussing. So you can, we have here the tables of the shifts and the coupling constants, and however we can also have the chemical shifts on top of the peaks. or you can have them, we can have the numbering on top of the peaks and the numbering on the structure. Of course, you can have the scale in ppm or in hertz. Let's stay with ppm. If you decided that you did what you wanted to do and you want to go back to the full size, you just click to go back to full size. Also of interest is the integral line, so you may click here and you get your integral line. The final thing here has to do with showing the grid lines. So right now we have the grid lines shown, but for some reasons you may not like the grid lines, so we remove them. Okay, now to more important parameters than these cosmetic ones. First is the frequency. By default, the spectrum is predicted for a 400 megahertz system. But if you want to predict it for another frequency, you can select it here. So if you want to see how the aspirin spectrum would look on a 900 megahertz system, you select 900 megahertz, and after a little bit, you see the spectrum as it would appear on a 900 megahertz. You see here we also have a little wheel, which is the properties, the options, and here is where you define the options for line width and coupling constants to be used for the calculation. So the common line width is set to 1 hertz, and the NHs and OHs are set to 5 hertz. By default in the calculation, we are not using J's more than 3, so if you want to include 4J and 5J, you need to tick this. And it's also helpful to select show only values greater than 1 hertz. Mostly because if you set your line width to 1 hertz and you set to see couplings below 1 hertz, you will not see them. By default also, we select to have couplings with fluorine, with phosphorus, and with other nuclei. Okay, I would not really recommend you to change any of these, mostly because you will probably not have any better resolution. If you have reasons to believe that you have better or worse resolution, you can come here and change it. Okay, so the moment I click OK, the spectrum is recalculated for the new settings and displayed again. Okay, so this is the prediction of the proton NMR spectrum. And let's say that you want to predict the carbon NMR spectrum of the same compound. You don't need to re-enter the structure. You just click CNMR. And after a little bit, the carbon spectrum is presented. In the same sense as before, you can zoom and see peaks more clearly. And the same functionality again, you go back to full scale, you go on the peak, you see the atom corresponding in the structure being highlighted, as well as the lines in the relevant tables. There isn't anything else to customize on the carbon spectra because it is assumed that they will always be single lines, as all carbon spectra are recorded with proton decoupling. Now let's see an example of predicting a fluorine NMR spectrum and another way of loading a file. So I'm going to upload a file with structure information, and I'm going to click this icon, and I select the file from my list here. So I think this one has a fluorine or a nitrogen. So the moment you click OK, you see you have to wait a little bit until the actual file appears here, and then you click Send File, and again it tells you success file is valid and was successfully uploaded, and you click OK, and after a little bit the structure will be loaded there, and what's taking time right now is that it's calculating the carbon spectrum. So we need to wait a little bit. There you go. So we have the Lipitor molecule, and we have the carbon spectrum calculated. We see that we have here a fluorine atom, so we can go in the fluorine NMR predictor, click fluorine, and it will calculate the fluorine spectrum, and you will see only one peak here. Now you see that the scale here comes by default as as hertz, so you may want to go to ppm. And yeah, so you just have one fluorine atom, so you won't see anything more here. Since this molecule also has nitrogen, we can go ahead and predict nitrogen. And after a little bit again, we get the nitrogen spectrum. Again, the scale appears in hertz. We set it to go to ppm. And here we have two peaks. And we see the chemical shifts as -225 and -250. Now, an interesting point here is the reference for nitrogen. So by default, it's using the chemical reference, which is nitromethane. If you want to have the chemical shifts for the more common or the biology reference of ammonia, you select ammonia, and then the chemical shifts change to values that are what should be for a reference of ammonia. Again, of course, the same thing. You go on the peak and you see the table highlighted, and you also can go on the structure and see both the line on the table and the peak on the spectrum highlighted. Okay. Now, in all of these ones, all of these spectra that we have been predicting, we saw this download report button, and if you click this, you will get a PDF report with the spectrum, the structure, and all this information. I'm not going to click it now. Yeah, the other option for pasting, for adding a structure is to paste the molecule from the clipboard. So you may have a structure drawing tool, for example, ACD ChemSketch, and you have a structure here. You can go and select your structure and copy it. And now you go back to iLab and you click paste. And after a little bit, you see the structure appearing here and the corresponding spectrum predicted. Okay, again, keep in mind that the paste functionality will not work if you are using Chrome as your browser. Okay. Finally, if you have a smile string, you can click here and enter the smile string, and this will automatically convert it to the structure. Okay, so I don't have a smile string right now. Yeah, okay. Okay, it asks me for one. Let's generate a smile string. So here we go. I can go edit and copy, and I can go here and paste it and hit return. And the structure is added. Now, in all these structures that you are uploading, pasting, or converting from smiles, you can always go here and edit them. And also, another thing I should mention is that once the spectrum is predicted and the structure is shown here, if you go on the window, structure window, and move your mouse wheel, you can make the structure bigger or smaller. This could be helpful if you have some very big structures. Finally, the last thing to talk about is the databases, the databases that we have here. So we can click the carbon NMR database, and by default it will search the whole database to find the exact structure to what we drew. There is nothing here, so you can select something else. Let's say, for example, similar structures, and search. This may take a little bit of time because it's searching through a very big database of structures, and after a little bit you get here a list of similar structures. You see it's more than 1,000 similar structures that it found. I mean, no wonder, this is a rather common molecule there. And if you now go and click on any of them, you get here information about that particular entry in the database. So you get the formula, the name, molecular weight, masses, the full list of chemical shifts, and you also have a reference of where was this structure and this spectrum reported. What kind of spectrum was it? In this case, it was a depth spectrum at 50 megahertz for carbon, so this was on a 200 megahertz instrument. In the same sense, you can search the database, you can search the proton database, or you can search the carbon and proton database. So let's go again for similar structures. So here we will get results for, I should click search. Here we will get results for both proton and carbon chemical shifts at the same time. While before we only had carbon, and if I had clicked here, I would have had only proton. So here we go. So right now it found 460 molecules with entries in the carbon-proton database with similar structures. If I click on this one, I see now two columns, carbon shift, proton shift, again with a publication. Okay, if I click on the next one, I see another one. Okay, so that's mostly what I intended to present to you today. So okay, if you have questions, you should type them on the question box right now, and they will we will answer them as they appear. Okay, I see one question appearing. What is the maximum molecule size we can have? So what is the biggest molecule we can enter? To begin with, you cannot enter huge big molecules. You can enter small molecules. The whole prediction algorithm works only for small molecules, and small molecules by default are considered to be the ones with 200 heavy atoms or less. The problem is that even though in principle you could use these methods for predicting chemical shifts for bigger molecules, if you go for bigger molecules, then it is mostly through space effects that dominate the actual observed chemical shift than the through bond ones that are used here. So in reality, you can. I've tried with small peptides, and they work maybe up to 9 or 10 amino acids. So that's probably the maximum you can go. You cannot enter, for example, a protein. Other questions? Yeah. So see, yeah, what elements are allowed? In principle, the elements you can use are the ones that that appear here. So when I select to draw the structure, and I have these elements, these are the ones you can use. So you can not use, for example, organometallics or anything else funny. Also, you cannot use salts or whatever. So you need to have, let's say normal organic molecules. And on a relevant question here, what abbreviations are allowed? So we see here that we have CH3 or whatever, so can I use any abbreviations? The answer here is generally, unfortunately, no. So you cannot use any abbreviation you may think. You can use the abbreviations that are included in the IUPAC table of abbreviations. And ideally, you should try to avoid using abbreviations. So even something like CF3 may not work. You have to explicitly define a carbon with 3 fluorines. Okay, how to make a nice output picture with good resolution. The best way to do this is to, actually the only way, is to generate the PDF report and copy it from the PDF file. This is not a program that will generate, for example, a vector graphic for inclusion in journals. For this, you could use the desktop software from ACD Labs that will allow you to export file that you can resize infinitely or whatever. This is the ACDI lab is just to help you with your everyday prediction needs. I see another question: how good are the predictions comparing to other methods such as DFT and ChemDraw? Well, the ACD lab predictions are widely considered to be the most accurate one in the field. We have the biggest database of around, I think, 350,000 compounds. And over the time, several people have tried to compare our predictions with predictions from other pieces of software, and we were always better. Okay, so the best way, to answer the question for yourself, since you do not have to believe what I'm saying, is to try it out and see, to begin with, how different is the prediction versus the other software, and how accurate it is in the end in comparison to the actual experimental data. I am sure that you will find out that the predictions are by far the best you could have. Here another question. Can we calculate spectra for mixtures? The answer is no, you cannot calculate spectra for mixtures. So if you enter here 2 molecules, then only, I think, the biggest one will be calculated. In fact, the smallest one will be removed. Again, on the desktop software of ACD predictors, you can calculate spectra for mixtures. Okay, Kiera?
Okay, yeah, well, so thanks very much for that, Dimitri. It's very helpful. And if there were no other questions, then I guess we'll just say that, again, ACD iLab is available to anyone in the UK at an academic institution, and if you go to access it from your university network, you will automatically be able to access it. If you'd like to access it from off-campus, you can log in via Shibboleth, or you can send us an email and we'll set you up with an off-site password and username that you can access it from. And if you have any other questions in general, you can email us at cds@rsc.org for the chemical database service. Hello? Can you still hear me?
Hi, Kiara, I can hear you.
Okay, thanks very much for coming to the webinar. And we'll have another one next week looking at some of the other tools with ACD iLab. So do come along to that. Thank you.